This is a poem about the Platonic solids. Now, what's a Platonic solid? Sorry about that. What's a Platonic solid, I hear you ask? Well, it's a regular convex polyhedron in three-dimensional Euclidean space. And a regular polyhedron means that all the faces are congruent regular polygons, all angles and all edges equal, and the same number of faces meet at each vertex of the polyhedron. And if it's convex, it means that all the vertices come out rather than in. They're all hills rather than hollows, so it's convex. And we say three-dimensional Euclidean space because that's where we live, and there are analogues of the Platonic solids in higher Euclidean dimensions. In four-dimensional space there are 6, and in five-dimensional space there are 3, and in all higher dimensions there are 3. But we will leave those for another time. The Platonic solids are named for the philosopher Plato, as you might guess, and in three-dimensional space there are only 5 of them. The regular tetrahedron, which is 4 three-sided faces, equilateral triangles, the hexahedron or cube, which has 6 four-sided faces or squares, the regular octahedron, which has 8 three-sided faces, the regular dodecahedron, which has 12 5-sided faces, and the regular icosahedron, which has 20 three-sided faces. And it's fairly simple to prove that there aren't any others. Here's one, which is the cube, regular hexahedron, and here's another, which is the regular tetrahedron. Now, an interesting thing about the Platonic solids is that, along with many other polyhedra, they exhibit or possess the so-called Rupert property. And what this means is that if you've got 2 identical ones, you can construct a hole through one of them that the other one will pass through. This is named, it's not named for Rupert Bear, it's named for Prince Rupert of the Rhine, who predates Rupert Bear by about 300 years. As he was born in 1619 and Rupert Bear was born in 1920. Excuse me. Now, Prince Rupert asked if you can produce a hole through a cube such that an identical cube will pass through the hole. And the answer is yes, you can, as was shown at the time by the mathematician John Wallis. And actually it's fairly easy to show, and you don't have to be as clever as John Wallis to do it. It's exercise in trigonometry for any schoolgirl or boy. But anyway, this poem refers not to the property called Rupert, but to the property called duality. And if you have a Platonic solid, and if you mark the center of each face, and then you join each of the centers of adjacent faces with straight lines, you will produce another Platonic solid inside the first one. And then if you do the same thing again, mark the centers of the faces on the one you've produced, join with straight lines, adjacent faces, you will produce another Platonic solid, which is the same as the first one you started with. So you go from the first one to another one, and then to the first one again. And that property is called duality, and the solids are said to be duals of one another. Okay, the poem goes like this, and I should say that all the solids referred to are understood to be Platonic solids, though it's not explicitly stated every time. So, poem goes like this. Said the dodecahedron, how cruel, with the icosahedron, by rule of the fortunes of fate, I can never be mate, though we're each one the other one's dual. Does the earth perform actions tectonic? Are their oral sensations symphonic? Ah, would that it were so, but the answer is no. Our relationship's purely Platonic. Then the cube spoke up, Lord, love a duck. I'll say I get the same kind of luck. Octahedron and me, our liaison can't be. At least not when it comes to a meaningful relationship. Tetrahedron said, no love or pelf stops you guys being left on the shelf. But see, I'm my own dual, and now that's really cool, 'cause I just go and play with myself. The end.